Okay, great. Before we start the next session, I just want to introduce you to Tom Bufano, who's the Vice President of Research here at Boston University. He's going to say a few words.
Hi, welcome all. I'm Tom Bufano. I'm the Vice President of Research here at Boston University. I came in time to hear a lot of Uri's talk, and this is precisely why I've taken this job for a year, because it's just an absolutely inspiring thing to be here and to see all of this, this great work. I'm especially grateful to David and Swathi and Matthias for putting this event together. This has been this is the second year for this program. In doing my research for coming here today, I saw that EEG is exactly 100 years old, and I thought, wow, that's another wonderful thing to think about, that in 100 years of EEG, it's made a certain amount of progress, and then the advent of AI and neurophotonics and FNIRS is changing that at a very rapid rate now, and I'm very excited that Boston University has both the neuroscience and the computation and AI that put us in a great position for leading in this area. I'm delighted that you're all here. I am grateful on behalf of Boston University that you took the time to come, and I welcome you to the event. Thank you also to the Chen Institute for their sponsorship of this event. That's really rewarding for us, and we're grateful. Thank you so much.
Thank you, Tom, and thanks for the support of all the centers at the university. Also, in addition to promoting a lot of discussion amongst all of you academics, we also are encouraging industry to join in our interactions and discussions. I just want to call out, we do have 4 companies here who are going to have posters tomorrow. You can go and see their posters, but I just want them to stand up so you can find them today and tomorrow before their posters. There's Buoy. Is there a representative from Buoy? And forgive me if I'm saying your name wrong. They are not here yet. How about Fundamental Optical Solutions? They're not here. They'll be here tomorrow. Nerex. I know Nerex is here. They're a maker of FNIRS instrumentation. They're there. So if you're interested in FNIRS instrumentation, find them. VeriSense is VeriSense representative here. They'll be here tomorrow. Okay. So excellent. Do look for Nerex, at least today. All right. So now on to our first oral session. This is Neuroscience and Everyday Life Activities and Disorders. We have 3 speakers in the session. They have 25 minutes each. We'll try to cut them off then so that we can then have 5 minutes of discussion after each talk. First, we have Julia Kline from National Institutes of Health, and she's going to be talking on baby steps to deciphering the neural basis of walking.
All right, good morning, everyone. Thanks so much for having me here today to discuss baby steps toward deciphering the neural basis of walking. I prepared these slides with the help of Dr. Diane Damiano at the National Institutes of Health. I've been part of her lab for 3 years, and I'm going to review a decade of research into these topics from our lab and from others. So our lab at NIH, the NAB lab, combines biomechanics, physical therapy, neuroscience, and neuroengineering, with the primary goal of improving mobility in children with cerebral palsy. We have a strong focus on neuroimaging technologies, especially the use of emerging technologies. We also use mobile brain imaging for assessment, training, and as an outcome measure in our studies. So for those of you who aren't familiar, cerebral palsy is a group of disorders stemming from an early brain injury. The hallmark of this disorder is a mobility issue, with 70% of those with CP eventually learning to walk, albeit with great difficulty sometimes. So walking is a major neurorehabilitation goal in this cohort. And it is the brain mechanisms that underlie mobility disorders, such as CP, remain poorly understood. And this may be due in part to the limitations of traditional neuroimaging modalities like MRI and diffusion tensor imaging. So this may be due in part to the limitations of these modalities. So especially MRI, it's claustrophobic, it requires specific equipment and processing, and subjects are required to lay in a supine position, and MRI itself is highly sensitive to small movements of the head. So it makes it more amenable to studying small motions of the extremities, but definitely not naturalistic motions like gait. And about 50% of children with cerebral palsy are not able to be imaged in MRI at all due to a heightened startle response and also due to involuntary motions. So we believe that some of these gaps in neuroimaging can be filled with EEG and with functional near-infrared spectroscopy, or FNIRS. These two modalities are the oldest and youngest modalities respectively. EEG was first used in 1924 by Hans Berger, so this year actually marks its 100th anniversary. And recent advances in hardware and software, including small portable EEG amplifiers, have enabled its use in whole body mobile tasks such as locomotion. And the same goes for FNIRS. Each technique, though, has its own strengths and weaknesses, which I'll get into a little bit later. But these weaknesses can partially be overcome when using them in combination. So over the past century, there have been several theories put forward about the neural control of locomotion. In 1910, Sherrington et al. Theorized that peripheral reflexes control walking. The next year, Brown suggested that walking is controlled by rhythmic activation in the spinal cord, in the spinal networks. However, at the time, this did not catch on. In the 1970s, there was a resurgence of interest in the idea of central pattern generators, or reciprocating spinal oscillators, that control interlimb coordination. During the same period, it was shown that cats whose spinal cords had been surgically severed at a level that eliminates communication with the brain would walk automatically when they were placed on a treadmill. So I'll show you what that looks like. So if you change the treadmill speed, if you speed it up, they actually speed up as well. So this indicates that the spinal cord has the ability to generate these patterns independently of descending cortical control. So this caused a resurgence of interest in treadmill training after spinal cord injury in humans. So early studies showed that humans could walk on a treadmill after spinal cord injury, and this was groundbreaking. However, the training took months, and not all individuals were able to successfully learn. So that's why most published studies are single-person case studies. And the theory was that bipedal locomotion is just more complex and more slowly evolving. For instance, humans don't walk immediately after birth, like some animals, and our motor system develops gradually throughout the first several years of life. So here's a quick rundown of the studies that we've done on brain activity during walking and other locomotor-related activities in our lab. We're going to go through each one. So here, healthy adults walked on a treadmill on 2 separate days, one day with NIRS and one day with EEG. And we examined if the two modalities provided complementary information. So NIRS tracks the bold signal, which is an indirect measure, versus EEG as a direct measure of the electrical activity of the brain. So the top plots here show NIRS activation, which is mainly medial, and that aligns with the location of the lower limbs in the motor cortex. The top left plot shows group level activation, or HBT, in red, across pairs of NIRS channels. And we see bilateral activation, which is shifted slightly toward the dominant hemisphere. And then that right panel shows the HBO data projected on the cortex. And on the bottom row, we're showing the strength of EEG activation across the entire cortex, broken out by the alpha and beta bands, which are important frequency bands for human motion. So next is our EEG treadmill study on active versus passive speed changes. Our goal was to see when the brain was most active. So this data here is from the passive condition. When healthy adults walked on a level treadmill at a single self-selected speed, and these are the 4 major brain regions identified in the study. Activity occurred in the prefrontal cortex, the anterior cingulate, the sensory motor area, and the posterior parietal. And each circle that you see represents a single individual who had activity in one of these 4 regions. And here we're looking at the EEG activation during the gait cycle for a single individual. This is one of the strengths of EEG over NIRS. EEG has exquisite temporal resolution, and you can measure the amount of activity and also the connectivity in sensory motor brain areas and precisely time it to the gait cycle. So though it's not shown here, the active treadmill condition showed more activation, more neural activation than the passive condition. So this is when I think our group and other researchers in the field realized the cortex was much more active during gait than originally thought. So here you should be seeing a young child with cerebral palsy walking on the treadmill, but unfortunately this video is not cooperating. What you should be seeing is that he is walking with random speed changes, and he clearly needs to be physically and mentally engaged, and that in turn is reflected in his brain activation. So we now believe there are actually 3 main components underlying gait. We have peripheral spinal reflexes that are activated by sensory input. We have spinal oscillators, and we have supraspinal commands, and all 3 of these interact with each other. So this is a great quote about how gait is controlled. Human locomotor control is not organized as in reaching to meet a predominantly kinematic specification, but is hierarchically organized with a semi-autonomous peripheral oscillator operating under episodic supervisory control. So what this is saying, it's basically describing the brain as not just continuously active during gait, but interjecting only when it's necessary. So now this is our first study of EEG in cerebral palsy. We had 9 participants with unilateral cerebral palsy and 10 with typical development walk on a treadmill. And unilateral CP involves just the arm and leg on one side of the body, similar to a stroke. And we examined the relative power in the dominant and non-dominant hemispheres. Red is rest and blue is walking. On the left side, you see the typically developing group. There is a drop in power when they go from standing to walking in both the dominant and the non-dominant hemispheres. And interestingly, the kids with CP showed a lower baseline power during standing, but they had an equivalent drop in power with activation. Another interesting finding from this study concerns the peak mu band frequency within the hemispheres in both groups. So the mu band is 10 to 13 hertz over the sensory motor cortex, very important band for human movement. And our CP group had a significantly lower peak mu than our typically developing group. And the mu band in healthy individuals or typically developing individuals shows an increase in peak frequency in the early years of life. And we believe that the fact that individuals with CP showed a lower peak frequency indicates that they are exhibiting delayed cortical maturation. So here we're looking at activation in 2 children with unilateral CP. One kid is showing bilateral activation, and the other is showing unilateral activation. And this really illustrates the value, I think, of EEG during walking to understand the specific mechanisms at play here for each child. So these children actually looked identical and were scored identically from the outside. They both had a GM-FCS of 1 and similar walking patterns, but their brain activation was completely different. So we've just started to look at bilateral CP in children and infants. These kids have much poorer mobility, and it's harder for them to walk on a treadmill without holding on relative to unilateral CP. And this population is actually the most likely to stop walking in adulthood, which makes them an important target for rehabilitation. So what I'm showing here, which some of you may be familiar with, it's called an event-related spectral fluctuation in EEG power over the gait cycle. So blue is desynchronization or reduced power, in the mu 10 to 13 hertz range, that indicates increased cortical activity. In the few subjects we've collected so far, we see a pattern with more activity in the dominant hemisphere in the mu band, so side A, there's more blue. The difference is not to the same degree as unilateral CP, but it does differ from typical development. And so these kids are developing their brain activity in the presence of a brain injury. So each kid comes up with their own solutions, and patterns can look very different from subject to subject. So we're currently collecting even more data to better understand the brain activity in this population. Here's a nice quote that sort of sums up those preceding two slides. Each child had their own unique neuroanatomical and neurophysiological profile, which is even more apparent for those with brain injuries. So moving on now to our NERS work, we are one of the first groups to do NERS in the motor strip. And this is just an example of looking at the motor strip, the sensory motor area, and plots of significant activation for kids squeezing a ball with typical development versus their twin who had bilateral CP. So they're both squeezing with the same hand, but you can see that the opposite side of the brain from what you would expect is activated in the child with CP. Okay, so here's our paradigm for a lower extremity task, complete with the music we played. Our participants performed 8 blocks of activity for 20 seconds each, and rest of variable duration in between. We used that visual and auditory stimuli that I just played to cue the movement and keep them engaged, which also increased brain activation. So we enrolled 14 participants with bilateral CP. We know that kids with CP have trouble controlling their limbs, and that issue is often worse distally. So that's why we did a range of lower limb tasks, but I'm going to show dorsiflexion and recumbent cycling tasks, which really focus on that distal extremity. So our NERS dorsiflexion results are shown here. The first plot on the left is the typically developing kids, who mainly show inhibition on the ipsilateral side. We don't really see much activation on the contralateral side in this group, but it's a very simple task. The kids with the milder impairments, those that are considered GMFCS 1 and 2, have some differences from TD. They showed a little more activation, but they were not significantly different from each other. But the real stark difference can be seen in the children who had the greatest difficulty walking. So at the far right, you see the children who are GMFCS 3. Their whole motor cortex was activated dramatically during this task. So to see why this might happen, here is a child with GMFCS 3 trying to dorsiflex just the ankle shown in blue. But as you can see, they're also dorsiflexing the other ankle and moving the rest of the lower limb and the hips on both sides. So for this group as a whole, the number of muscles active during dorsiflexion was significantly correlated with the number of active brain channels, which suggests that more brain activity is directly related to more muscle effort. And then here are our results for unilateral and bilateral cycling. Again, typically developing children had the least activation. GMFCS 1 and 2 aren't significantly different from each other, but they did have more activation than typical development. But again, for GMFCS 3, that more significant impairment level, the activation was high across the entire cortex. So one of the major differences you see across the tasks is that for TD and those lower GMFCS levels, bilateral cycling is the preferred movement pattern because it's what we're so used to doing. You know, we never cycle with one leg, and we never walk on one leg for that matter. So that's why we believe we see a lot of deactivation during bilateral cycling. But that difference, again, disappears for GMFCS 3. Both tasks take high level of effort for these kids. So we're starting to get preliminary data on FNIRS in infants with CP. And here's a cute video of a little girl walking on a treadmill. This is what our day-to-day experiments look like. Okay, like I said, we're starting to get preliminary results here. Initially, we did a study where we combined NIRS and EEG on the same cap and collected them concurrently. So here you see that concurrent NIRS and EEG activation for the left and right motor areas in a typically developing 3-year-old. And we see event-related activation across the gait cycle, which is cyclical. The highlighted portion, again, shows the alpha and the low beta frequency ranges, which are involved in gait. And this child shows rhythmic synchronization and desynchronization, time-locked to the gait cycle, which is similar to the pattern that we see in adults. Not quite identical, because this is just, it's emerged and it's being reinforced now. The NIRS activation here, which you see in the bottom, the HBO, tends to be more medial than lateral, but it seems to be similar to an adult pattern. And then here now is some preliminary data from a 10-month-old with CP who isn't yet walking independently. We can detect emerging activity that looks similar to the 3-year-old, but it's not nearly as strong. It's in the lower frequency bands, and we believe that's because coordination is just starting to develop, and this skill is just starting to emerge. More data collections here are ongoing. Okay, so in addition to using EEG to assess brain activity, we can now use it in real time for neurorehabilitation. So we're currently working on a brain-computer interface neurofeedback paradigm that detects a user's intent to move in real time and it detects their intent to dorsiflex in real time, and it triggers functional electrical stimulation to the tibialis anterior, which assists and helps them move through that motion. So for the 4 children who have already completed this study, we've also used EEG pre and post to look at changes in the brain activation. And this work is also ongoing. And if you want to read more about these topics, there have been 2 recent reviews. The first discusses using brain imaging techniques to understand neural correlates of gait in healthy individuals. And the second is a review from our lab that discusses the neural correlates in CP. So in conclusion, FNIRS and EEG are well poised to advance our understanding of brain activation during movement and neurological disorders, and to measure changes in response to training. These aren't easy things to do, and at present the methods are imperfect. It takes a village to do this. We need therapists to engage with these children. We need engineers to develop new and better analysis techniques. And we need commercial partners to develop better hardware and improve data quality and ease of use. So one thing we recommend that we have done is to reach out to experts in the field. For example, when we were doing our NIRS work, we had several conversations with David Boaz, and he was very gracious with his time and helped us move forward. So Diane especially wanted to extend our thanks to him, as he was instrumental in our work. And I wanted to thank you all for your time and attention, and I'd be happy to take your questions.
Thank you, Julia. We have ample time for questions. So please, come up to the microphone. Questions. I'll start off the first question. I was really curious, the deactivation you saw in the typical developing deactivation. I mean, that is relative to baseline. And so there.
Are you talking about the EEG deactivation relative to baseline?
So if I interpreted your talk correctly, the HBO was decreasing during walking in the motor area.
Right, so the deactivation was specifically for that bilateral cycling, and that's why we kind of introduced this idea of the tripartite control of locomotion and locomotor-like activities. So we believe what's going on is that something like reciprocal, bilateral stepping is almost entirely under spinal control. So there's not a lot of top-down supraspinal commands. It's a really good question. I mean, these are kids, so they could have been making small fidgety motions. I mean, they're not entirely still. They're sitting and watching a silent video, but yeah, that's my guess.
the people online, I'm sorry. The EEG connectivity, could you say a little bit about how that analysis is done?
Yeah, absolutely. So that is an analysis we did using the Source Information Flow Toolbox, the SIF toolbox that's available in EEG Lab. So that is basically looking at the strength of connectivity. And so you can, do all your pre-processing, you can epic the data around an event of interest, like a step in cycling, and then you can look at the strength of connectivity in really whatever frequency band you want. Here, I think we're looking at the alpha and the beta connectivity between hemispheres.
So it's just looking at a correlation or coherence.
Exactly, yeah, and you can pick what connectivity measure you want. I think that may have been directed coherence I was showing.
Got it, thank you.
Yeah, first of all, thank you for your talk. I think, is this on? I don't know. Yeah, it was really nice. I have a rather methodological question about the combination of FNIRS and EEG. You said that you did that in the same cat, basically. How did that work out for you?
Not super well, which is why we have moved away from that. So initially, yeah, we really wanted to get that concurrent activation to see how these play together. But unfortunately, doing that, you're losing some real estate over the motor cortex. And anyone who's ever worked with EEG and independent component analysis, which I didn't have time to go into, probably understands that you need a nicely distributed array of electrodes that covers the entirety of the sphere of the head. So we did feel like we lost a bit of resolution having to compete for the real estate with the NIRS electrodes. So that's why we moved to same subject, but 2 different days for the 2 modalities.
Ah, nice. Thank you.
Do you think there's a solution to doing it?
Absolutely. That's why we wanted to advocate for better hardware solutions. We used a cat from Brain Products that was sort of already, they had started to tackle this problem about how to integrate the 2 arrays.
Yeah.
But smaller sensors, higher density arrays, these are all things that could help.
Okay, great.
Great talk, thank you. So could you speak a little bit to the neurofeedback for CP, and if you did anything for adults, or is it just for children?
Yeah, absolutely. So far we've only looked at individuals 21 and under, so teenagers and young adults for the first 4. But we actually did publish our first case study about a year back, and our first subject came in and did 13, I believe, sessions with our neurofeedback device, and we tested him before and after to see if he improved range of motion, to see if he improved his dorsiflexion ability. And this particular individual, so we tailored the paradigm to their goals. This individual was an 11-year-old with unilateral CP who was pretty functional and loved to play baseball and just wanted to run the bases a little faster. And after 13 sessions with our BCI, he was actually able to dorsiflex further, so his range of motion increased, and his walking speed increased as well. And he was, that's the quantitative data, but qualitatively, he was super happy. He said his therapist was really happy with the change too, so it's really great to be part of that.
Thank you. That was really interesting, and thanks for doing the really hard work. This is not easy work to do. My question sort of takes off from what was asked earlier. Do you, think that the increased activation in the kids with CP, you pointed that it relates to higher muscle activity. So is it a combination of increased muscle activity that relates to increased brain activation, or is brain activation effort different from increased muscle activity? I hope my question makes sense.
It does. So I think that's a really complex thing to untangle, and that's part of why we're doing this work. But we do think it's kind of a combination of increased muscle activation and also increased difficulty.
Yeah.
So we talked about the brain sort of in these cyclical lower limb activities, sort of interjecting only when necessary. One of the areas that tends to be active during these tasks is the anterior cingulate, the brain's error monitoring region. Yeah. And so part of it is also, this is really challenging. So you're monitoring your trajectory, you're probably trying to recruit more muscles midway, you're trying to do all these things that in a typically developing person just comes very naturally. So yeah, I think a combination of increased muscle recruitment and just increased sort of cognitive load to try to accomplish this task.
I was thinking the same thing, and so the B part of my question is, as these kids with CP get better, improve, you would expect to see a decrease or a normalization of those connections, these hyperactive connections you're seeing, or
I
is
think
the
so.
trajectory different for them?
I think so. It's hard to say because, like I mentioned, every kid sort of solves this problem differently. So our preliminary results, we've sort of looked at lateralization to see if things are shifting more to the side we'd expect to see the activity on. And yes and no. For some kids, it seems to have that pattern, that they're learning to sort of take on a more typically developing pattern. But we've had other kids sort of just double down on their divergent pattern and, activate the side that isn't injured, more. There's more activation. And that also seems to be a viable way to do this in some individuals. So it's a great question. I wish I could give you a definitive
Well, that's
answer.
fascinating.
But
So there are different ways for the brain to compensate. One might
Exactly.
be like typically developing, but other might end up being maladaptive from the brain's purpose, but functional for the child.
exactly, yeah.
Okay, thank you very much, Julia, for the great discussion.
Thank you.
We'll move on to our next speaker.